Hello, you're very welcome into this video. My name is Sean, and on top of being a principal in SND Methods and the lecturer of engineering in the Southern Regional College in Newry, County Down in the north of Ireland, this year I'm an academic advisor for the Southern Regional College's STEM racing competition team entry, team called SCAR. SCAR is made up of 5 level 3 engineering students that I do also have the privilege of teaching calculus of all things too. On top of all that, I am an open wheel racing car enthusiast of all formulas, not only Formula 1, but certainly into Formula 2 and Formula 3 and whatnot. And I have, since 2003, having graduated with a degree at that time in mechanical engineering, have always been enthused by fluid dynamics. And had in the years subsequent to graduation and prior to becoming involved with the Southern Regional College, had the good fortune to be able to be involved with a lot of computational fluid dynamic applications and evaluations, both in external and internal flow applications. So bringing the academic supervision and my own background together with respect to this team, I would be to the fore in ensuring that the team gives due consideration to the impact of aerodynamics and their design choices on the aero performance of the car. A lot of description on a STEM racing car is that it is a miniature Formula 1 car. Now, whilst I concede that certainly and broadly, maybe it does resemble a miniature Formula 1 car, albeit scaled down, but geometrically and as far as features go, there is similarities. The function of a lot of the features of the Formula 1 car that are replicated on the STEM racing car are completely different, are the reasoning for them. So before I get more into that, this particular video here is going to be the first in this series, and this series is to will be of videos concerning itself with the front wing of the car. I will do more series after this, and in fact I have a series with subsequent series dealing with maybe the rear wing, the side pods, the rear pods, and so on. The front wheels again, which will be hugely important. But the front wing within this series is going to be massively important because it is the first part of the car that encounters the air. So not only is it going to influence that point of interference between the car and the air, it's also going to have a huge influence and factor on the air and on the air's performance and the format and the flow field of the air aft of the wing and how that interacts with the rest of the car. Now, going back to what I had started with respect to the STEM racing car being a miniature Formula 1 car, I do see that many design their front wings, initially at least, to resemble Formula 1 front wings. And why not? Because they look absolutely phenomenal. They look class. However, the reason Adrian Newey designs a front wing for a car, and the reason for a Formula 1 car, and the reason why Jimmy or Mary is designing a front wing for the STEM racing car should be completely different. The Formula 1 car wants downforce, at particular speeds, and it wants to shed downforce at other speeds. In the STEM racing car, we're only really going to be at, broadly speaking, one speed, even though we are accelerating from an initial of 0 meters per second up to a top speed. The format, the profile is the same. It's akin or analog to the main straight, where Formula 1 itself, previous to the 2026 regulations and the active aero, had a specific system to shed downforce called the DRS system. It got rid of drag and by effect got rid of the downforce. That's where we are. The objective in this here is not to have drag, just like a Formula 1 car on a main straight, which means we cannot have downforce. If we do not want downforce, then we do not want a multi-element complicated, large, or relatively deep plan form wing. So what is it that we do want? That's the question. So that's really what I want to dive in on this first video. The second video that we'll do is we'll go on and we'll set this our design, or our design choice or proposal we'll set it up for a computational fluid dynamic, or CFD analysis, and then subsequent videos we'll look at the results of that, and perhaps after that make a couple of tweaks to see where we might be able to improve the aerodynamic performance in elements that mightn't necessarily be favourable from our own evaluation and what has come to light by looking at the results of the post-process results of the CFD analysis. So the front wing. Where do you start with this? Well, the place that you're always going to start with this here will be on the STEM racing regulations. So if you go to whatever jurisdiction that you're operating in, us in the north of Ireland are racing in the UK STEM racing competition. If you go to that site, and generally if you go to the resources, and if you come into all resources for this site, we scoot down here to the bottom. There is a section for the regulations. Right, we're not moving so fast here. Just going to pause this. No need. Here we go. Resources, rules and regulations, STEM race and primary regulations. I'm going to focus on the professional class. There's professional class technical regulations. I'm going to click the download here. All right. Move this over to this side here maybe. And whenever this document eventually does come up, I am at home here. It's a place called South Armagh, and sometimes at the best of times the bandwidth wouldn't just be where I'd like it to be. But however, once it's converging on 100%, we're going the right way. I'll just pause it and wait for this. Okay, back again. It's eventually come down. So here we are here into the STEM racing regulations, the technical regulations for the professional class. And what I'm going to do is I'm going to zip this up a wee bit on the screen. We can see it a wee bit better. If I come down to Article T8, I see the nose, the front wing, end plates, and wing support structures. So within this here, if I scroll on ahead down, we can see the front wing. We see two different elements here. We see a multi-element, it's called a multi-vane on this one, and we see a single vane or a single element front wing. This is given the spans, or the regulations for the spans. But in this video, what we're going to do is we're going to look at a 2D flow over the airfoil first, and maybe even bring in some mesh independent study for it. But it will be done in 2D before we move on ahead into the 3D. So in that vein, I'm going to ignore these spans, and I'm going to come down into the section here, the chord, okay, the T8.6.2, the front wing chord. Now, something worth looking at here, and certainly something worth speaking about, is this here. Like if you look at the chord there, and again, if I could zoom in to this, I think it would be absolutely brilliant. I can see a chord, I can see my airfoil in here, which is this stretched ellipse. Okay, and what the chord is showing here is given a distance from the foremost point, or the 4-point here on the leading edge, to the aftmost point here on the trailing edge, and it's measured the distance straight down. Now there's a slight contradiction here in that a chord is given as the distance from the foremost point on the leading edge to the aftmost point on the trailing edge, and it would generally be measured along the center line, or the mean chord line there of the airfoil. This is being measured normal or perpendicular to the track surface, and I can just notice that this airfoil is slightly pitched. There's an angle of attack on it. So the mean chord line on this here, the chord line itself, is not parallel with the track, yet the vernier caliper here is measuring it as if it was parallel to the track. Now, with such a slight angle of attack there's not going to be very much between what the chord line measured chord is and what this technical document's measured chord is. This chord here, what it looks to be effectively the cosine of the angle of attack as opposed to the foremost point to the aftmost point. Yeah, so maybe it's just something to clarify there. Should this wing be parallel to the ground, if indeed the vernier calipers are to be measured as if they were normal to the ground themselves. The multi-element here does not have that problem. Each one of these have a zero angle attack by the look of it. And I see the vernier caliper again is normal to the ground, and given that these have a zero angle of attack, that leaves that they are parallel with the ground, which would say that the chords with these, this is like a composite chord length of the multi-vane, would be probably a better indication of what the chord is, maybe more so than this. But again, I stand to be corrected, but if there is any doubt at all in these scenarios, ask the judges, ask the evaluators, or the competition organisers. There's no point saying you thought whenever there's points being deducted. Everybody always has the ability to ask the questions. But regardless, the chord is to be between 15 millimeters and 25 millimeters long, and we're going to have some sort of a shape like this. Now, this must be on it. All right, that's part of the regulation, is that you must have a front wing and the end plate as well, again to resemble the Formula 1 car. I would rather not have a front wing on it because of what our force design considerations are going to come in. Right? If you run anything through the air, you're going to have a viscous effect. Right? You're going to have drag on it. If there's no front wing, there's no drag by the front wing. It's less drag that we have to deal with, but it has to be there. So the objective on this here is to minimize the effect of the drag on this. Again, we're not looking to generate downforce on this, so there's no reason why we should have an induced drag. So an induced drag is that element of drag that we have whenever we're looking to get a lift or a negative lift, or a lift or a downforce. Where we need that, it's more important, for instance, for an airplane to have lift than to have no drag, because if it doesn't have lift, it can't fly. So it has to put up with the fact that it's going to have drag by virtue of the fact that it needs to lift. Not only are these cars here running down a straight track at a relatively low velocity compared to what an airplane is doing, they're tethered to the track, so they're not going to lift off the track. We don't need the downforce to keep them down. If anything, we'd like a wee bit of lift maybe to reduce some of the rolling resistance and take the wheels off the track and just let it fly down the track. But for rigor and for good practice, we don't want that to happen either. So we don't want downforce and we don't want lift. What we really are looking to have is some sort of a neutral profile on this here. No angle of attack, and but definitely a symmetrical airfoil with no camber in it. So getting in a little bit onto that, perhaps, what airfoil do we choose then? Right? What profile here, what shape are we going to choose if all that is to be true? Well, that comes into looking at airfoils themselves. So if you go into airfoil tools, and you can do a Google search for that. We have airfoil database search, airfoil tools, and I'm just going to go to an NACA 4-digit generator here. Now, if I go to an NACA, I have a 4-digit airfoil generator. NACA is the forefather effect of NASA. And the NACA ran a series of tests on a range of different airfoils and measured not only critical Mach numbers, but also lift coefficients and drag coefficients at a range of different velocities, air velocities. And they categorize a lot of their own airfoils in accordance to 4, and in some cases 5 digits. The 4 digits are a very common one across the board because they're easy enough to interpret. The 4 digits, what we have in here, the first digit of the 4, in this case here, is a 2. That is what the maximum camber is. And broadly speaking, again, these are defined in the NACA report number 824. But the camber is broadly speaking how much curve does the airfoil have? No, how curvy is it on the top or reversed if it was on the bottom? That's what the 2 is. This one here as a 2 curve. Now, and there you are, max camber percent 2. If I change that to a 4, right, and hit plot, and we look at what's going to happen to this airfoil on the top, right, we can see it's curvier than the last one. Right? There's more of a curve across the top here, and even the bottom curves a wee bit as well. Right? Again, I'll go back to the 2. There it is there. It's less of a curve. I say it's heavier, it's fatter. It's not really. It's just less curvier. It's more of a symmetrical shape along the chord line. Now, the second number, the 4, right? That's the max camber position, right? So where does that camber happen? So if we were to look at this airfoil here, and I look at this black line here, which coincides with the foremost point of the leading edge, and this last green line, which corresponds with the aftmost point of the trailing edge, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 divisions. What this is saying, if we go 40% down of this, right, which will be 1, 2, 3, 4 here, this line here, right, at this position, this is where the max camber on the airfoil occurs. Right? If I was to put in a 2 onto that, plot it, right? We can see here where it is. Look, see the camber line up here? It's moved so far forward. Look, it's up here, and you could see kind of the wee bit of the shape turn here, where 40% moves that kind of that bump back a wee bit, smooths it out, and possibly you could say makes it a little bit more streamlined, maybe more continuous. So that's the 4, and then the last 2 digits go in a group. There's the 12, and that's the thickness. So that is the thickness in percentage of the chord line. So if this was 100 long, okay, the thickness of the airfoil there would be 12 millimeters. If this was 200 long, the thickness of the airfoil would be 24 millimeters. It's the 12%. Okay, so thickness is a consideration that we want to look at. All right, chord length, we'll consider that in a second, but let's consider thickness. So if we look at, if I come on into this airfoil consideration, and what I have here is if I was air myself and I was coming into the front of the car, and I have an airfoil of air coming on, and if I was to consider that against its wee mate here, it didn't square up, and I have air coming on. I can extend this out like so. And of course this air supply, this airflow would come into 3D as it goes into the board. It's intuitively clear that there's going to be more air resistance on this bigger, heavier block than there is on this thinner block. Okay, so there's a pressure drag here. If I was to look at this head on, if I was to look, if I was sitting on the air and I was fast approaching this airfoil, and I look straight on, this was my front wing of my car. I want to make that as soon as you can. And I was heading into this. Well, all the air was coming on into this and into this. Right? The chances that I would hit this one here are much greater than the chances that I'd hit the bottom one. I might hit both of them, sure, but this is a bigger face. I'm more likely to hit it. This one here I might miss. Some I might go over the top or under the bottom. If I was a wee bit up, I might miss this one, but if I was a wee bit up, I might still hit this one. So what I'm going to do is I have a heavier frontal area on the airfoil. The more stoppage, the more that the air is going to stop. So just again looking at it side on, airflow coming over the two of these. Let's keep this up on the top one. Right. Air coming on to this, air coming on to this. Right. We're certainly going to have air flowing over it. And same with this one here. We bump there. We bump there. But what we will have is a big dead spot there. Here, the dead spot, or the kind of stagnation point with the air hits, is much smaller. So we've less pressure drag. So first consideration, let's make our wing as thin as possible to reduce this pressure drag. So if that's the case, I go back onto my airfoil tools here, and there's a 12. I would ideally like to make that 1%. Is there such thing? 2401, look at that. Yeah, there is. That is a wee curve in it, but let's go for it. I'd probably be great, but the problem was it would probably break. Okay, how are we even going to fix that onto the car? And the other thing about it is something that we'll get into the next couple of videos and towards the end of this. How do we test if what we're getting out in the computational fluid dynamics is accurate unless someone has empirically or experimentally tested a similar airfoil that has true values of how this performs? We can't just take the results that we get out of our own computational fluid dynamic analysis and assume that they are right. In fact, we should assume that they are not right, that they're incorrect. Like, we should be our biggest self-critics when it comes to computational fluid dynamics, and you know, I suppose in contravention to the stance taken in legal regimes, assume that our results are incorrect. You know, that we are guilty unless otherwise proven to be correct. So yeah, 2401, that'd be absolutely phenomenal. But I don't want to camber on this either. Why? Why don't I want to camber? Well, that takes in another thing there about an airfoil. Okay, so lift and downforce are generated by a multitude of different effects. Some being inertial effects, you know, where we're looking at Newton's laws there. Okay, so Newton's effectively third law on that. And the other bits there, of course, are the Bernoulli principles. So a lot of people, I think most, will always talk about Bernoulli principles first, because it gives a better explanation of why airfoil surfaces are curved. Right. And the reason is here that when you're coming over a curved surface, this flow here accelerates. So I'm going to keep this short because we could do other videos and we can talk about this for hours. The curved flow accelerates. Right? The curved flow comes up and then accelerates over that. Some people will tell you there it's I can't even mind what they call the reasoning for it, but they reckon that for some reason that this streamline here, this path line, and this here, these were partners. They're inseparable. They love each other. And this one here was sent over the top, and this one was coming underneath. And because this one here has a longer path, it needs to go faster so that the two of them can romantically join again on the aft side of the airfoil and live happily ever after downstream here somewhere. That's completely incorrect. Okay, so if you hear that, if it was me, I would just ignore it. That I don't think that top path line or streamline there cares at all what the one underneath it did, and it has no reason to meet it at the aft side of the airfoil. The fact of the matter is that over the top section here, okay, over the top section here, yes, there is a longer path, but there's a series of physics that happen on there, which accelerate that flow over that. And this accelerated flow, by Bernoulli's principle, results in a reduction of pressure. Now, there's another thing in that as well. There is also schools of thought which talk about the air being pinched there, because this bump in it here just drives the air up into what would be otherwise non-affected streamlines up here. Now, in fact, they are affected for multiple chord lengths up above it, but at some point there they don't. But there is a wee bit of a squeeze in there as well, which contributes to acceleration. But broadly speaking, accelerating flow translates to reducing pressure. And that's, is it Johann? One of the Bernoulli brothers. Bernoulli says that. So reducing pressure, what happens is the offset of reducing pressure. Reducing pressure means right, that if we still have a higher pressure down here. All right, so let me just pack up some of these in here. So if I have a big high pressure here, or just say ambient or unaffected pressure, relatively higher pressure, and this pressure here has lowered, right? That pressure on the top there has lowered, right? Then, because of the pressure gradient, that airfoil is going to want to rise up towards the lower pressure. The high pressure will push it up. Okay. If you flip that upside down and you put the curve on the bottom, and then you have the exact same effect, except now the oncoming air is accelerated underneath the bottom. Where the stuff on the top, probably can get a wee pinch in there as well, because I want this to broadly go over the top. Right. Let me just get a big white line here to indicate that I intend to have the two of them separate. But what we have now is the same idea. We have the accelerating flow on the underside because it's turned upside down, and on the top side here what we have is the relatively, well, it is affected, but I'm going to say relatively unaffected. It's still a higher pressure air. What we do have is the lower pressure air here, and by virtue of that, that's more over there underneath the airfoil. But because we have the high to the low, what we do now is the pressure, it's going to push it down, and we have negative lift or down force. Right. Now, the angle of attack, I'm not ignoring it. Right. I completely appreciate that the angle of attack and the inertial forces of that air, the momentum on the air, hitting the airfoil and pushing it down does also contribute. I totally get that, and I'm totally agreeable with that, but we're just not going to talk about it now because I'm only trying to explain the curve, not the angle of attack. So that's why you have a curve. So if that's the curve is to generate downforce by the Bernoulli effect. I don't want downforce or lift, as we said. We'd want this to be neutral. So that means that I don't want any camber, 0. And if I have no camber, this here should also go to 0, max camber position. Look at that there. Completely symmetrical, very thin airfoil. Now, that would be phenomenal to work with, but we'd never be able to fix that to the car, right, given what our plan area is going to be. So what we need to do is we need to up the thickness to make it structurally sound and maybe to make it fit something. So what does actually fit? All right, so here's standard airfoils that are in the database. Why are they important? Well, they're important because we can generate grid points for them. Now we can for this as well. But what is massively important for us to do, as I said, is also to make sure that what we carry out our CFD on, we have empirical data, or else other people's CFD data results, that has been backed up by empirical data. But we need to make sure that our data is correct. Does anybody have data for a 0001 airfoil? Well, not that I know of. I wouldn't have even thought that's such a thing as an airfoil. But I do know that people have data for a 0009. This has been tested not only by people but by organizations. I go for a 0009. Is that right? So it is a symmetrical airfoil. There's no camber. So we should be generating the same amount of accelerated flow above and below, which should give us a net pressure of 0 on both sides, one relative to the other. But the 009 is a airfoil that's been widely tested. There is a 008 in it, but I'm not aware of them being tested. Where has the 009 been tested? Okay, well, we'll go for the 009 in the first place, and I'm going to show it to you, but then we're going to move swiftly away from it, and I'll explain to you why. A lot of places here, they say, oh, this is an NACA airfoil, which incidentally, people might say NACA, they might call it a NACA. Now, I have it on good authority that it should never be called NACA. That it should be called the NACA, and of course that there has been written in black and white, not only by NASA and people who have done research on the history of the NACA, but more recent publications as well, which gave that the initialization of it, or the acronym NACA, is intended to be pronounced NACA as opposed to NACA. But there you are. Maybe it's NACA is just generally accepted as a NACA 0009 or 0009 airfoil now. But forgive me if I prefer to keep calling it an NACA 09. That's why. But anyway, if we did go to the NACA themselves, I have a paper here. Now you can get this on the NASA website as well. Airfoil data. There is the NACA report number 824. Okay. And in this here is a summary of airfoil data. Now, the airfoils that have been tested, this also gives the explanations in excruciatingly more detailed presence than what I gave. But if I would say definitely make yourself to some level familiar with this. It looks daunting. It is difficult, but that said, if you have any even mild interest in aerodynamics, there's some absolutely phenomenal data in that there. So have a look at it. Now, if I take myself on down to here, past the critical Mach numbers, and I come into this section, aerodynamic characteristics of various airfoil sections in section 5, and I look at what has been tested, I could see, voila, there is the NACA 0009 airfoil on 132. Yes, the 0006 is there, but why didn't I go for it? We'll get into that now in a second. The NACA 0009 airfoil is on page 132. Right, so me taking myself swiftly down, what are you telling me on page 132 here? Which one's this here? That's a 006. That's a 009 airfoil there. In the NACA report number 824, you will get this data. On the left-hand side, you get the section lift coefficients, and on the right-hand side, you get the drag coefficients. We're primarily going to be concerning ourselves here with the drag coefficients for the airfoil, more so than the lift, in that we're looking to ignore the lift. But even at 0 angles of attack, there'll be a level of lift. There are multiple plots on these traces here, and they correspond to different Reynolds numbers. So for instance, the circle is at a Reynolds number of 3 million, 3.0 by 10 to the power 6, where the square is at 6, the diamond's at 9, triangles at 6 with standard roughness. This AC position is the aerodynamic center, and that has more to do with the moment coefficient here, these graphs down here. Now, I'm not going to use this data whatsoever. Okay, I'm just saying the NACA have tested this airfoil, but this data here is absolutely useless to me with respect to my CFD calculation. The reason for that there is the Reynolds number that it's been tested at and the speed that it's been tested at. So it's massively important that any student that's coming into STEM racing and is going to talk to the judge about their decisions on aerodynamic features understands the Reynolds number. So the Reynolds number there is the ratio of inertial forces to viscous forces. It's a non-dimensional number, which is generally given by the density of the fluid multiplied by the velocity of the free stream I want to go for, as opposed to the near the wall. And on flat plate theory, it's going to be the characteristic length, right, L, and that there is over the dynamic viscosity of the fluid that you're running in, dimensionless number. So we are running in air, where our density will take as 1.225 kilograms per meters cubed. Our velocity, we're going to leave that blank just for now, right? Our characteristic length, leave that blank just for now, and our mu, we're going for 1.8 by 10 to the power of minus 5 Pascal seconds. Right? That's dynamic viscosity of air. V and L are going to be very specific to our application, which we'll get to in a wee bit. But for flat plate theory, any RE that is greater than 500,000 is turbulent flow. Right? And then therefore, if it's under 500,000, it's in a transition region, but broadly defined as being laminar. And so RE, which is less than 500,000, it's far less than 500,000, it's going to be laminar, but as it approaches 500,000, it moves into transitional. So there are sections of it, even as low as 50,000, an RE of 50,000, which have turbulent characteristics, especially when we look at the likes of our laminar separation bubbles and things like that, which will be hugely impactful with our STEM racing characteristics. V and L, I need to know what my Reynolds number is. I need to know what V and L is. Right. So for V and L, what I can say is that my velocity, I want to get this car down a 20-meter track as fast as I can. The world record, I believe, is 2016 is at 0.916 seconds. It is below 1. And I don't think it was broken last year. The 1 second was broken last year, but it certainly was broke was it, I have one here. Maybe I don't have it there now. A YouTube video, I just had checked them, and at 0.995 could have been got there as well by an Australian team a couple of years ago. But roughly speaking, we want to get this down a 20-meter track in about a second. Okay, so our velocity then is that I want to cover 20 meters, right, in 1 second. 20 meters per 1 second. Right. Ideally, I'd like to get 21 meters a second, 22. But we'll go for 20 and just play it conservative. Now the length, what is the length? This is my chord length in this case here. Right. So yeah, you could take it there really as the surface length over it, but for a very thin airfoil there and small sine angle, you can estimate that to be the chord length. So I'm going to say L. Just going to put a note in here where L can be estimated by the chord length. What is the chord length? Well, if I go back into my technical regulations, I need to go into Adobe. I thought I had them tech regs open. Maybe not. Bear with me, everybody. I'm sorry. Let's go down to this here again. Hopefully, it won't take us long to open this time. Unreal. It does. Let me just pause you again. All right, brilliant. Back again. So here we go. My chord length. So the chord length must be between 15 and 25 millimeters. So what we'll do, just to be safe, is we'll take an average and let's go for 20 millimeter chord length onto that. So my length here is going to be 0.02, and then of course is in meters. So that leaves there that the Reynolds number for our application will be 1.225 kilograms per meters cubed, multiplied by, I'll tell you what I'm going to do, just leave out the units just to make it up a wee bit quicker. 1.225 by 20 by 0.02. Let's divide that up by 1.8 by 10 to the power minus 5. Alright, so let's see, can we work out what we have here? That's 1.225 multiplied by 0.20 mil multiplied by 20 meters a second divided by 1.8 e to the minus 5. And I'm getting 2.722 by 10 to the minus 4. Alright, 7.7722. Sorry, folks. 7222. Apologies. Let's write it out in larger numbers. Let's see, just in full. 27222 is my Reynolds number. Now, that's my Reynolds number at 20 meters a second. Now, 20 meters per second is only an average velocity. We don't start off the starting line at 20 meters a second. Right? We start off the starting line at 0 meters a second, and 1 second later we're 20 meters down the track, which means at some point, if we've achieved that, we also are going to have achieved a velocity of 40 meters per second. By 10 to the power minus 8. So this here is obviously going to be doubled, which is what, 54,444. That's at 40 meters per second. All right. So that means we could say there that we're going to accelerate. Our acceleration is going to have to be about 40 meters a second because we're getting down the track. We're getting down the track in 1 second. From a starting point of 0. Right, so our average velocity is 20 because we started at 0. So the only way our average velocity can be 20 with the starting at 0 is if our final velocity is 40. Now indeed it could be above 40 because this is going to be an accelerating graph. And as well as that, we're assuming a constant acceleration on that there as well, which might not happen. These are being driven by an 8 gram CO2 cartridge, so there's nothing to say that the thrust being generated out of that force that's being generated at the starting gate is the same as what it is at the end gate. But regardless, we have these two Reynolds numbers. These are laminar by all accounts. So at these Reynolds numbers, even the higher one there, the flow regime, that's the airflow regime over that wing, is laminar. Laminar flow is completely different from turbulent flow, and the models to solve them and the mathematics to model them are completely different. All right, so in the NACA report number 824, that's giving us test results there for turbulent flow. They will not apply to our application. I've had people say to me, oh, well, look, the Reynolds number is dimensionless. You can increase your velocity, or maybe increase your chord length to bring it up to 3 million. Right? You're at on your higher thing of 40 meters per second. To be safe, we'll probably run with that. you're at 54,000 there. You know, like if you brought that up 20 times by 360 times, you know, you could achieve what they have in the NACA. Yeah, maybe so, but that would be in no way as indicative of what would be happening on track. So what good would that be to me? I can carry out a mesh independent survey. I can say my physics are right, but they only right for turbulent flow. I'm going to have a different model, right? I'm going to be running a different model, not a turbulent model, like a gamma Reynolds wall function and so on. That will not apply on a turbulent application. So I cannot use that. So that NACA document here is so widely used, but for a stem racing application, it's not really where you want to be. Where do you want to be? Okay, well, what I would suggest people look for in here is look at the SHALIG. You see SHALIG here, University of Illinois, airfoils at low speeds. It goes 1984. SHALIG conducted a number of tests on airfoils at lower Reynolds numbers, and within what he had then was Reynolds numbers, I believe, at 40,000 or 60,000. He skipped 50,000, right enough, but you know, we're not a million mile off there. But a lot of these were being done for lower velocity vehicles, and if you look at research papers now, Otaki specifically, an awful lot are being done in Japan for UAVs, you know, for propellers on UAVs which have velocities which are very similar to what are encountered in stem racing applications, and they are doing very good work and carrying out and publishing results of experimental tests on airfoils used for propellers in these. But nevertheless, there's volumes published, and these are available online, and also on the UIUC website. You'll find a lot of this information. Bear with me here. If I go to UIU website, this is it here, the Applied Aerodynamic Group. There's the coordinate databases for a range of different airfoils as well. But we will take these from the airfoil tools. But certainly, the incomplete guide to airfoil usage, there is a plethora of absolutely phenomenal resources on that site, and it's definitely something to get broadly familiar with, if you can, if not very familiar with in a detailed way with sections of it. But nonetheless, airfoils at low speeds. So here we go. Here's the airfoils that were tested. Airfoils in volume 1, and if we look down through what we have a test here in volume 1, I can see right smiling bang there is an NACA 0009. That is brilliant. Right, there is an NACA aerofoil there in 0009 there. Okay. 2, there is another series of airfoils tested as well, and 3, and so on. Now, what you can do is you have sorted lists given here as well, and what we can also do, if you bear with me, I don't think it's actually in this one here, but in the airfoils at low speeds document, which is in it. Yeah, this gives similarly good data to what was in the NACA report number 824 on the performance of airfoils and individual airfoils and findings of them. Right, they're all published there. It's brilliant. So if you choose the NACA 0009 for test purposes, make sure you refer back into this as well. All right. So we have an NA 0009. I'm going to choose that because it has a low frontal area on it, cross-sectional area, and I have test data available for it. All right, let me just see if I can actually find the test data for that. NACA. So here it is on page 140 of the PDF, the NACA 0009 airfoil. And there we have it there. And when we come on to the subsequent pages on it, what we can see is its performance. There's coefficient of lift at different angles of attack at a Reynolds number of 40,000, which is greater than our average Reynolds number, but it is also lower than what our assumed maximum Reynolds number is, if indeed we cross the finish line at 40 meters per second. And of course there, this one is slightly above it. We will be focusing broadly on the zero angle of attack section here, where we can generally see that our lift is zero. At that point, maybe slightly above it, wee bit of lift on it. But that again is the coefficient of lift at them two angles of attack, or at them two Reynolds numbers, and there's coefficient of lift at 80,000 and at 100,000. And then we're moving on to the NACA 6409. Now, right enough, where's the drag? We're not seeing drag on this here, but that's okay. What all we're looking to do is we're looking to get confirmed test data at a Reynolds number that we can test using our model, our solver, and our wall functions for the laminar flow regime. We can tune our velocity to match a Reynolds number of 40,000 or 60,000, and all we're really looking to do is to make sure that our CFD results are broadly indicative of what's found here in this empirical test data. And if it is, we know that our solver is probably solid, our geometry solid, and very importantly there, that our mesh is solid. And from that, we could proceed on to mesh independent study to make sure that any sort of discretization errors are going to be, I suppose, taken out, resolved out by virtue of the fact that our mesh is going to be resolved to a suitable factor. So we do have test data. We do have test data for the 0009, and that's what we're going to run with, again, because it is the lowest profile, lowest frontal area of any of the airfoils that we have test data for. Now, sure, we probably can find something that's maybe 8% or 6%. I couldn't find one there that was also symmetrical at them smaller thicknesses, and as well as that, we don't really want to get too thin either, because this still has to retain structural integrity. Okay, so I'm going to drop away down at this, and let's return ourselves into the airfoil tools. So there's an NACA 0009 airfoil, and what I now want to do is I want to get coordinates for this, because I'm going to move on ahead and I want to bring this into a computational fluid dynamic analysis, set up the physics there to replicate the test conditions and validate both my setup, my functions, and my solver, and my mesh is adequate. And when they are, we can then get some good insight, good results, and good insight into our into the performance of an NACA 0009 airfoil for our front wing. Well, I'll deal with that one in the next video, taking the coordinates of this and moving this into the geometry file. So until then, thanks very much for watching. I really do hope that this was a benefit to you. And I'm not just saying it, but I really would be interested in hearing if what I had said to you with respect to choosing an airfoil, whether it be considerations from the physical principles of it, with in respect to its thickness and this and that, or the availability of test data to validate any numerical results that you might have. If it has affected your design choice, I'd like to know, just from my my own peace of mind. So thanks again for watching. I hope you did enjoy it. I hope you did take something from it, and I hope you have maintained a level of interest that'll take you into the next video when we look to model this. So thanks for everything. Thank you.